we are going to first study about the total probability rule for the multiple events. We already learned about the total probability rule, but in this case, we are going to discuss about the multiple events. If E1, E2, blah, 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 Ek are K mutually exclusive and exhaustive subset, the probability of the event B equals to the probability of the intersection of B and E1 plus the probability of the intersection of B and E2, blah, 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 plus the probability of the intersection of B and Ek. And this can be explained by this Venn diagram. If we assume that we have a sample space here, and as was discussed here, these values are K mutually exclusive, so we can express that as E1, E2, E3, Ek, okay? And if we assume that there is a subset B here, this is the subset. This will be the intersection of B and E1, right? And this part will be the intersection of B and E2, right? This part will be the intersection of B and E3. And this part will be the intersection of B and Ek, right? So in this case, the probability of the subset B equals to the summation of the probability of the intersection of B and E1 and the probability of the intersection of B and E2 plus the probability of the intersection of B and Ek. And as we already learned, the probability of the intersection of B and E1 can be expressed as the conditional probability of B given E1 multiplied by the probability of E1, right? And plus, this also can be expressed as the conditional probability of B given E2 multiplied by the probability of E2 plus this will be the conditional probability of B given Ek multiplied by the probability of Ek. Okay? So that's why the probability of a subset B can be expressed by this equation. For the case that E1 from E1 to Ek are mutually exclusive. Okay? That is the total probability rule for multiple events. And this is the typical example when K equals to 4. Okay? So this is same Venn diagram with this one, but the K is just 4. So based on this total probability rule for the multiple event, we are going to solve the example 2-28. That is for the semiconductor contamination. And in this case, what is the probability of failure? And to understand this example, we can simply use the tree diagram. And we have the probability of failure for the left column here. And we have also the level of contamination. And also we have the probability of each level of contamination. So first we can think about the level of contamination here. we have three levels of the contamination, right? First one is the high contamination, and we have medium contamination, and also we have low contamination. And each case has the probability, right? The probability of high contamination is 0.2, right? From this table, okay? And the probability of medium level of contamination is 0.3. That is, the probability of M equals to 0.3, okay? And the probability of low level of contamination is 0.5. So the probability of L equals to 0.5. And also, we have another probability of failure. This is the probability of failure, or the failure, or non-failure. Okay? We have two options. First one is the failure or non-failure. So in this case, we have two options. First one is the failure, F, and the other one is non-failure, okay? But in this case, we can have the past probability of failure when there is a high contamination, right? So that is conditional rule, right? So the conditional probability of F given H equals to 0.1 here, right? This is the probability of failure when the high level of contamination is obtained. And what is the probability that non-failure is obtained? There will be the conditional probability of non-failure given high level of contamination equals to 0.9, right? Because the summation of each conditional probability should be 1. So we have two different conditional probability here. And for the case of medium level of contamination, we also have two options. First one is the failure, and the other one is non-failure. Okay? So in this case, we also have to apply the conditional probability, right? Because the probability of failure can be obtained when the medium level of contamination is obtained. So the conditional probability of failure given the medium level of contamination equals to 0.01 here, right? And the conditional probability of non-failure given medium level of contamination equals to 0.99, right? In this case, we have to obtain the summation of these two conditional probability should be equal to 1. So 1 minus 0.01 is 0.99, okay? And in this case, we also have two options. First one is the failure, and the other one is non-failure. And we can apply the conditional probability as well. So the conditional probability of failure given low level of contamination equals to 0.001, right? So in this case, the conditional probability of non-failure given low level of contamination equals to 0.999, right? So that is the conditional rule. Okay? So in this case, what is the probability to obtain the failure when the high level of contamination is obtained? So we obtain the failure, okay, when the high level of contamination is obtained. In this case, we have to obtain the high level of contamination at the first time, right? And we have to obtain the failure, right? So this should be connected as AND condition. AND condition can be calculated by the multiplication, right? So the probability will be the conditional probability of F given H multiplied by the probability of H will be 0.1 multiplied by 0.2, that equals to 0.02. Okay? And also, we can apply the same concept to this one. The probability that there is no failure when the high level of contamination is obtained, that equals to the conditional probability of N given H multiplied by the probability of H, that equals to 0.9 multiplied by 0.2, okay? And that equals to 0.18. And we also can apply this concept to here, 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 right? But the question is that of failure. So we have to calculate only this, right? Okay? So in this case, we can have the conditional probability of failure given medium contamination multiplied by the probability of medium equals to 0.01 multiplied by 0.003. Okay? Okay? And in this case, we also can apply the same concept. Conditional probability of F given L multiplied by the probability of low level of contamination equals to 0.001 multiplied by 0.5, that equals to 0.0005. Okay? So the probability of failure will be the summation of 0.02, 0.003, and 0.0005. So the probability of failure equals to the probability of conditional probability of F given H multiplied by the probability of H equals to add the conditional probability of F given medium level of contamination multiplied by the probability of M plus the conditional probability of F given L multiplied by the probability of L. So that equals to 0.02 plus 0.003 plus 0.0005 equals to 0.0235. Okay? So that is the probability of failure from this table. Okay? So we can simply calculate the probability of failure using this tree diagram. And now we are going to discuss about the independence. If any one of the following equivalent statements are true, two events A and B are independent. First one is the conditional probability of B given A equals to the probability of B. And the conditional probability of A given B equals to the probability of A. And the probability of the intersection of A and B equals to the multiplication of the probability of A and the probability of B. So if you obtain these three things, we can determine that the event A and B are independent. So this means that occurrence of one event has no impact on the occurrence of the other event. Okay? So that is the definition of the independence. So from this definition, we can solve the example 2-28-9. This is about the case of sampling with replacement. Okay? A day's production of 850 parts contains 50 defectives. 2 parts are selected randomly, which means that equally likely. But the first part is replaced before selecting the second part. So let A denote the event that first part is defective, and let B denote the event that the second part is defective. So in this case, what is the probability of A and B? So the probability of A equals to 50 divided by 850, right? Because we have 50 defective among 850 parts. So the probability of selecting the defective at the first time will be 50 divided by 850, okay? And what is the probability of B? In this case, the first part selected is replaced before selecting the second part. That means we still have 50 defectives among 850 parts, right? So the probability of B equals to 50 divided by 850, okay? So in this case, the event A, the first selection, does not affect to the second event, right? The second selection. So in this case, we can call this is independence. So in this case, what is the probability that both are defective? Which means that the first part should be defective and the second part should be defective as well, right? So that is the question for this one. So the probability that both are defective can be calculated by the probability of the intersection of A and B. Why? Because the first and second part are connected as AND condition. Okay? The first part should be defective and the second part should be defective. In this case, we can say that both are defective. So the AND condition can be expressed as intersection, right? So there will be as we already know, the probability of the intersection can be equal to the conditional probability of B given A multiplied by the probability of A, right? So, in this case, what is the conditional probability of B given A? This is just probability of B, right? Why? The first part does not affect to the second part. So this can be rewritten as the multiplication of the probability of B and the probability of A. Okay? That is the definition of the independence, right? So that equals to 50 divided by 850 multiplied by 50 divided by 850. That is the probability that both first and second part are defective. So we can apply this independence rule to calculate some examples when we know about the independence of two events, okay? And this is another example. Are the data in table 2-4 independent or not? So to determine the independence of the data in table 2-4, we can simply apply the previous equation as I explained in the previous slide. And if we apply this third definition, we can determine the data in table 2-4 are defective, independent or not, okay? So firstly, we can calculate the probability of intersection of F and D. Firstly, we can think about this probability, okay? And what is the probability of the intersection of F and D? This can be rewritten as the conditional probability, right? The conditional probability of D given F multiplied by the probability of F, right? We know about this definition, right? And what is the conditional probability of D given F? That is 2 divided by 40, right? Right? So that is 2 divided by 40, okay? Because we can do 2 among 40. That's the conditional probability of D given F, right? The F is first obtained, and then we can obtain the D. So we can obtain the D among the 40. So this is the conditional probability of D given F, okay? And multiplied by the probability of F is 40 divided by 400, right? 그러니까 이 컨디셔널 프로바빌티 여기서 보면 이 F가 40개가 일단은 있어야 여기서 D를 뽑는 거잖아요. 그죠? 그러니까 2 나누기 40이 이 컨디셔널 프로바빌티의 확률이 됩니다. 아시겠죠? And so this will be the 40 is eliminated each other, right? And this is 2 divided by 400. That equals to 0.005, right? And if this probability equals to the probability of D multiplied by the probability of F, we can determine that the data in table 2-4 are independent. So, what is the probability of D? That is 20 divided by 400, right? So 20 divided by 400 multiplied by the probability of F will be 40 divided by 400. So in this case, 40 will be eliminated by dividing 400 by 40, and there will be 10 here, right? And the 10 can be eliminated by dividing 20 by 10, so there will be 2 here. That is 2 divided by 400, okay? And that equals to 0.005, okay? So as you can see, these two probabilities are equal. And we're going to have one another example. What about this case? The probability of the intersection of F and the complement of E. And this will be the conditional probability of the complement of D given F multiplied by the probability of F, right? And that equals to the conditional probability of D prime given F will be 38 divided by 40, right? So that is 38 divided by 400 multiplied by the 40 divided by 400. Oh, sorry. This is 40. Right? In this case, 40 is eliminated each other. And there will be 38 divided by 400. And if this probability is equal to the probability of D prime multiplied by the probability of F, we can simply determine that the data in table 2-4 are independent, right? So what is the probability of D prime? That is 380 divided by 400, okay? Okay? The probability of D prime. So 380 divided by 400 multiplied by the probability of F, 40 divided by 400 here. So in this case, 40 can be eliminated by dividing 400 by 40, and 10 will be left. And 10 can be also eliminated by dividing 380 by 10, so there will be 38 here. So that equals to 38 divided by 400. So as you can see, the probability of these two cases are equal. So we can determine that the data in table 2-4 are independent, okay? And this is the example, this is the explanation for the independence of the multiple events. The event E1, E2, blah, 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 EK are independent when, if, and only if the probability of the intersection of E1, E2, EK equals to the multiplication of each probability. So if you obtain this relationship, we can say that the event from E1 to EK are independent, okay? So this is another example to explain about the independence. This is the example 2-32. For the series circuit, this circuit, which is called 회로판 in Korean, operates only if there is a path of functional devices from left to right. The probability that each device functions is shown on the graph here. The probability that the left device is working is 0.8, and the probability that the right device is working is 0.9. And in this case, assume that the devices fail and operate independently. In this case, what is the probability that the circuit operates? This is the series circuit, right? The current in this circuit should be passing through the left device and the right device. So to operate this circuit, both of the left device, right device should be working, right? So these two devices are connected as AND condition, right? For this question. So how can we calculate the probability for this? Can be the probability of the intersection of left device and right device. Okay? But as you can see, it is assumed that the devices fail and operate independently, which means that we can calculate the probability of the intersection of L and R can be the multiplication of the probability of L and the probability of R, because these two devices are independent. Okay? So there will be 0.8 multiplied by 0.9 equals to 0.72. Okay? And this is another example. Example 2-33 for the vapor contamination. The probability that a vapor contains a large particle of contamination is 0.01. The vapor events are independent, okay? So if the probability of EI denotes the event that the ith vapor contains no particles, the probability of EI should be equal to 0.99, right? Because the summation of the probability that the vapor contains a large particle of contamination and that the ith vapor contains no particles should be 1. So the probability of EI equals to 0.99. If 15 vapors are analyzed, and what is the probability that no large particles are found? So to satisfy this question, we have to select the first vapor without contamination, right? And we have to select the second vapor without contamination. And we have to select the third vapor without contamination. And also, we have to select the 15th vapor without contamination. That is the definition of this question. So this can be expressed by the conditional probability of EI, E2, E3, blah, 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 and E15, right? And since the vapor events are independent, this can be expressed as the probability of E1 multiplied by the probability of E2 multiplied by the probability of E15. Okay? And what is the probability of EI? That is 0.99. Okay? So this will be the 15th power of 0.99, right? Okay? 이걸 지금 15번 곱했잖아요. 그죠? 이 확률 다 똑같고. 그러니까 0.99의 15승이겠죠. And there will be 0.86. And that is the typical example for the independence of multiple events. Okay? And this is another example for the parallel circuit. And this circuit operates only if there is a path of functional devices from left A to right B. Okay? And the probability that each device functions is shown in here. The probability that the top device is working is 0.95. And the probability that the bottom device is working is 0.95. So each device fails and operates independently. Okay? So in this case, what is the probability that the parallel circuit operates? So we have two options that the current can pass through either the top device or the bottom device, right? So these two cases are connected as OR condition, right? Right? 그러니까 일로 지나가도 되고 일로 지나가도 되잖아요. 그죠? 아까는 시리스 서큐잇은 이것도 통과해도 이것도 통과해야 되는데 지금은 이 둘 중에 하나만 통과하면 돼요. 그죠? 그러니까 OR 컨디션이에요. OR condition, we can express the OR condition based on the union, right? So this can be the probability of the union of T and B. So in this case, we all know about that this problem should be related to the independence concept, right? And in this case, how can we solve the union? Because we discussed about the intersection, right? To explain about the independence. So this should be changed to the independence relationship. So this can be the probability of sample space minus the probability of the intersection of T prime and B prime. Why? If we assume that there is a sample space here, this is the event T, this is the event B, and these two events are independent. That means there is no intersection here. So the union of the event T and event B will be this shaded area, right? And what is the probability of sample space? That is this shaded area, right? This is the sample space. And what is the intersection of the complement of T and complement of B? There will be this shaded area, right? The intersection of the complement of T and complement of B will be this shaded area. 그러니까 T의 컴플리먼트는 요거 B 펌에서죠. B의 컴플리먼트는 요거 펌에서잖아요. 그죠? 근데 인터섹션이면 양쪽은 하나씩밖에 없기 때문에 그 주변 면적만 되겠죠? 아시겠죠? So, if you subtract the intersection of the complement of T and B from the sample space, we can have the union of T and B, right? Okay? So, we can obtain this relationship from the Venn diagram. And so, what is the probability of sample space? The probability of sample space equals to 1, right? I already explained this part. So we have to calculate this probability. Each device fails and operates independently. This can be rewritten as the probability of the intersection of T prime and B prime equals to the probability of T prime multiplied by the probability of B prime, right? Based on the independence rule, okay? And what is the probability of T prime? That is 1 minus 0.95, that is 0.05. That is 0.05. Multiplied by, what is the probability of B prime? That is also 1 minus 0.95. That is 0.05, right? So that equals to 0.0025. Okay? So the probability of the union of T and B equals to 1 minus 0.0025. That is 0.0075. There is the possibility that the parallel circuit operates. Can you understand this part? So we can simply apply the independence rule for these types of examples. And now we are going to discuss about the Bayes theorem. Thomas Bayes was an English mathematician, and from the definition of conditional probability, as shown in here, the probability of the intersection of A and B equals to the conditional probability of A given B multiplied by the probability of B, right? We all know about this equation, but as I already explained that the order is not important, right? So this also can be expressed by the probability of the intersection of B and A, and this also can be equal to the conditional probability of B given A multiplied by the probability of A, because the order is not important. So from the second and last items, we can have the conditional probability of A given B equals to the conditional probability of B given A multiplied by the probability of A divided by the probability of B, okay? So this Bayes theorem can be applied, can be used when the probability of B is higher than 0. If the probability of B equals to 0, we cannot use this equation, right? So this Bayes' theorem enables us to solve the conditional probability of A given B in terms of the conditional probability of B given A. And this is the example. Example 2-36. From the previous example 2-27, what is the probability that a high level of contamination is present when a failure occurs? And this is the probability of failure. And this is the level of contamination. And this is the probability of level. So from this question, we have to obtain the failure first. And then we can have the high level of contamination. So if F denotes the event that the product fails, and H denotes the event that the chip is exposed to high contamination during manufacturing, this question can be expressed by the conditional probability of high contamination given failure. Okay? Okay? But from this table, we only can calculate the conditional probability of failure given high level of contamination, right? So we have to use the Bayes theorem. This can be changed to the conditional probability of F given H multiplied by the probability of H divided by the probability of failure. That is the definition of Bayes' theorem, right? So we have to calculate all these three things to obtain the conditional probability of H given F. Okay? So we are going to calculate the first part, that is the conditional probability of F given H, that equals to the probability of failure when high level of contamination is 0.1. That is the conditional probability, right? So that equals to 0.1. Okay? And the probability of high level of contamination is 0.2 here. Okay? And what is the probability of failure in this case? We can use the tree diagram again. Okay? This is the level of contamination. And we have two levels. First one is the high, and the other one is not high. Okay? And the probability of high level of contamination equals to 0.2 here. Okay? And the probability of not high equals to 0.8. Okay? And we also have the probability of failure. So in this case, we have two choices, failure or non-failure. And we have two options here, failure, non-failure, failure, non-failure. Okay? Since we have to obtain the probability of failure, we just can consider this two parts, right? So the conditional probability of failure given H equals to 0.1. And the conditional probability of F given not high contamination equals to 0.003. 5. Okay? So, the probability to obtain the failure when there is a high level of contamination equals to the conditional probability of F given H multiplied by the probability of H. That equals to 0.1 multiplied by 0.2. Okay? And the probability that there is a failure when there is a not high level of contamination will be the multiplication of the conditional probability of F given N multiplied by the probability of N. That equals to 0.005 multiplied by 0.8. So the probability of failure will be the summation of these two cases. So the probability of failure equals to 0.1 multiplied by 0.2 plus 0.005 multiplied by 0.8. That equals to 0.02 plus 0.004. So that is 0.024. Okay? So this, the conditional probability of high level of contamination given failure equals to 0.1 multiplied by 0.2 divided by 0.024. Okay? That equals to 0.02 divided by 0.024 and equals to 0.83. So the probability that a high level of contamination is obtained when there is a failure, that is 83%. 그러니까 어떤 걸 딱 뽑았어요. 파괴가 있는 것들 중에 뽑았는데 그게 하이 컨테미네이션이 있을 확률이 83%라는 거예요. 아시겠죠? 그 파괴된 것들 중에서 꺼내봤을 때 83%가 하이 컨테미네이션이다. 이렇게 계산하실 수가 있습니다. And now we are going to discuss about the Bayes theorem with total probability. If E1, E2, EK are K mutually exclusive and exhaustive event, and B is any event, we can obtain this relationship, okay? We have to first think about the Bayes theorem first. The definition of the Bayes theorem is the conditional probability of A given B equals to the conditional probability of B given A multiplied by the probability of A divided by the probability of B, right? There is a definition of the Bayes theorem. And in this case, what is the difference between this equation and this equation? If we change A here to E1, this will be E1, 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 right? If we change the A to E1, so from this equation, the only difference between these two equations are the probability of B is changed to the summation of all this total probability, right? So if we verify the probability of B equals to this, we can verify this equation. Okay? 차이점이 probability B가 요거로 변한 거잖아요. 그러니까 이게 이거랑 같다고만 증명하면 이게 지금 맞다고 볼까? 이게 맞겠죠? 그죠? So I will define the probability of B based on this this condition. If we assume that we have a sample space and we have E1, EK, and these are mutually exclusive, right? And in this case, if we assume that this is the subset B, okay, the probability of B equals to the probability of the intersection of B and E1 plus the probability of the intersection of B and E2 and the probability of the B, the intersection of the probability of the intersection of B and EK, right? And as I already explained, this can be changed to the conditional probability of B given E1 multiplied by the probability of E1, right? Based on the conditional rule. So this also can be changed to the conditional probability of B given E2 multiplied by the probability of E2. And this is the conditional probability of B given EK multiplied by the probability of EK. So the probability of B equals to the conditional probability of B given E1 multiplied by the probability of E1, blah, 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 and the conditional probability of B given EK multiplied by the probability of EK, right? And this is from this equation, right? So we verify the probability of B equals to this. We can verify this equation. Okay? So from this definition, it can be noted that the dominator, which is called 분모, is expressed as total probability. Okay? And the numerator, which is called 분자, is always one term of the dominator. Okay? Why? Because the numerator is one part of dominator. So this is the example, the Bayesian network. The Bayesian network are used on websites of high-tech manufacturers to allow customers to quickly diagnose the problems with products, okay? And a printer manufacturer obtained the following probabilities from its database. The probabilities of problems obtained in hardware is 0.1. And the probability of problems obtained in software is 0.6. And the probability of problems obtained in other things is 0.3. So from this example, we can have these three definitions. Software 0.6, probability of hardware equals 2.3. And these are the probability of obtaining problems, right? In hardware, software, and other. And probabilities of failure given problems, which is the conditional probability, right, of hardware that is 0.9, software that is 0.2, and other that is 0.5. So we have three other definitions, that is the conditional probability of failure given the problem of hardware that is 0.9. For the case of software, that is 0.2. And for the case of other, that is, there is F software, that is F other equals to 0.5, okay? So if a customer enters the manufacturer's website to diagnose a print failure, what is the most likely cause of the failure, of the problem? So how can we solve this problem? We have to find out the most likely cause of the problem when we see the failure, right? So we have to calculate the problem. This can be from hardware, software, other, right? Given failure. Okay? So we have to calculate the probability of hardware given failure, the probability of software given failure, the probability of other given failure. So when we calculate all these three things, we can determine which one gives the most likely cause of the problem. Okay? So to calculate this based on the Bayes theorem, okay? So we all know about these things, right? From here. But we don't know about the probability of failure. So as I already explained, from the tree diagram, the probability of failure can be the conditional probability of failure given H we can use this equation, right? 그죠? 저희가 트리 다이어그램 만약 그리면 첫 번째가 하드웨어, 소프트웨어랑 아덜이 될 거고 그 밑에 컨디셔널 프로버빌리티가 되잖아요. 그 토탈 프로버빌리티 찾으려면 이 두 개 곱하라 그랬죠. 그러니까 이 식으로 계산이 되죠. 그죠? 그죠? 이거 트리 다이어그램 한번 그려보세요. 그러면은 이 식이 나올 거예요. So this will be 0.9 multiplied by 0.1 plus 0.2 multiplied by 0.6 plus 0.5 multiplied by 0.3 that equals to that is 0.36, right? Okay? So we are going to calculate the first example, that is 0.9 9 multiplied by 0.1 divided by 0.36. That is 0.2 multiplied by 0.6 divided by 0.36. That equals to 0.5 multiplied by 0.3 divided by 0.36. And for each case, okay? So, from this calculation, we can determine that the other category is the most likely cause of the problem when we see the failure, okay? 아시겠죠? Because the probability of the other category is the highest one. So this is end of today's class. See you on Friday.